So, in the last lecture we saw how you could take system of linear first order homogeneous differential equations and write it in matrix form. You can write a system of linear differential equations that are non homogeneous also in matrix form. Okay. So, in that case what will happen is, instead of having dx by dt equal to Ax. Okay. So, this is homogeneous case, but in the case of non homogeneous equation you will have another term, the another vector b. So, this is also a matrix equation and b is a column vector. Okay. So, b is some column vector with those are the constants that make this equation non homogeneous. Okay. So, this is non homogeneous linear ODE with linear ODE system. It is actually a system of ODEs with constant coefficients. So, that would be the non homogeneous linear ODE system with constant coefficients. Okay, now, let us get back to the homogeneous system. So, the homogeneous case, so you have dx by dt is equal to Ax. Okay. Now, if x1 is a solution, that is dx1 by dt is equal to Ax1, and x2 is another solution, dx2 by dt is equal to Ax2. Okay. So, suppose you have two solutions x1 and x2 to this homogeneous differential equation. Okay. Then what you can easily see is, suppose I take C1 x1 plus C2 x2, okay, and now I put this in the differential equation. Okay, I call this equal to x prime. Okay. So, then you can see that dx prime by dt is equal to, so I can write it as C1 dx1 by dt plus C2 dx2 by dt, and I can write this as C1. Now, dx1 by dt is Ax1 plus C2 Ax2. Now, A is a matrix, okay, C is just a scalar, C1 and C2 are scalars. Okay. So, C1 C2 are scalars, A is a matrix. Okay. So, then I can write this as, I can take the A in front and I can write it as C1 x1 plus C2 x2. So, all I did was I wrote C1A as AC1, C2A as AC2. So, I can do this only because C1 and C2 are scalars, and so this is just A x prime. Okay. So, what you have is dx prime by dt equal to Ax prime, that means x prime is a solution. Okay. So, for homogeneous equations, so any linear combination of solutions leads to another solution. This is true for all homogeneous equations. All homogeneous equations, including those that do not have constant solutions. Okay. So, all homogeneous equations, and by all you mean not only first order, not only constant coefficients, So, if you have any homogeneous equation, you can write the general solution as a linear combination of any two solution. You can write you can take linear combinations of solutions and get new solutions. So, what we had was dx by dt equal to a times x. Okay. And now, if we take what we saw was that using eigenvalues and eigenvectors, okay, we obtained several solutions. So, x we wrote as x lambda e raised to lambda t, where a x lambda equal to lambda times x lambda. Okay. And so now the different, if lambda 1, lambda 2 up to lambda n and x 1, x 2 up to x n. Okay. So, these are distinct eigenvalues. Okay. So, the or you call them in quantum mechanics, you will come with a term non-degenerate. So, if these eigenvalues are distinct, okay, then I can write my x as a linear combination of each of these solutions. So, I can write it as C 1 times x 1 e raised to lambda 1 t plus C 2 times x 2 e raised to lambda 2 t plus C 3 times x 3 e raised to lambda 3 t, and so on all the way up to C n times x n e raised to lambda n t. Okay. So, this is the general solution. And it has n arbitrary constants. Okay. So, remember, if you just had a single differential equation, first order differential equation, you would have one arbitrary constants. If you had n first order differential equations, the general solution will have n arbitrary constants, and these arbitrary constants are determined by boundary conditions. Okay. Now, this is a case when all the eigenvalues are distinct. Okay. So, you can do this when the eigenvalues are distinct. So, now what happens if eigenvalues are degenerate? If two, I will just take the example of two eigenvalues are identical. Okay. So, that means when you solve for eigenvalues, okay, you find that two of the eigenvalues are the same. Okay. This is possible. Okay. Now, if you have two eigenvalues that are the same, then how do you write the general solution? Okay. You may or may not be able to find two orthogonal eigenvectors. Okay. So, if two eigenvalues are the same, so let us say x j e raised to lambda j t. Okay. So, this is one solution. Other solution you can write in this form x j e raised to lambda j t times cos C 1 plus C 2 t. So, C 1 and C 2 are scalars. Okay. So, what is done in this case is you take so if two eigenvalues are identical, Okay, then to find two solutions. So, one solution you take as x j e raised to lambda j t. Now, lambda j appears twice. Okay, so, the second solution with corresponding to lambda j is written in this form. Okay, so, C 1 and C 2 are scalars and these are chosen to satisfy ODE. Okay, so you basically you choose the appropriate values, so that they satisfy the ODE. So, you try this form of solution and then you put in the equation. Okay. So, so we will discuss all these in more details when we do some practice problems. Okay. But basically there is one other important message in this whole approach. Okay. So, this is, see, suppose you have dx by dt equal to Ax, we can imagine a trial solution x is equal to x equal to e raised to lambda t times some vector. Okay. And you can imagine trying a solution of this form. Okay. So, this is some vector. Okay. And what you can do is suppose you try a solution of this form. Okay. Then we find that Ax lambda equal to lambda x lambda. Okay. So, what I wanted to say is that you can also think of method of trial solutions Okay. This is something that will be used regularly. So, in other words, what I want to say is, suppose you have a differential equation. So, it is dx by dt is some matrix times x. Okay. You can imagine that you try a solution of this form and then you get the eigenvalue condition. Okay. So, that is one of the things that we did here was we tried a solution of this form and then finally you will get some conditions for C1 and C2. Okay. So, the method of trial solutions is something that is used very regularly and in all differential equations, not just first order differential equations, and this is something that we will see on we will see very often as we solve different kinds of differential equations. I will end this lecture here. In the next lecture, we will recap all the things that we have learnt in this module, okay, and then we will conclude with some practice problems. Thank you.